Chemical Science section of the Hungarian Academy of Sciences, it is my greatest pleasure to welcome you to the first chemistry lectures of our academy. I will be your host tonight. My name is András Percel, and I'm a professor of structural chemistry and biology at Eötvös Loránd University, Budapest. And at present, I am the chair of the Chemical Science section of our academy. The idea and concept of Christmas lecture is that in the middle of Christmas preparation, let's slow down. Let's dedicate some time and focus on important things such as spirit, science, and soul. This year is special due to COVID-19 pandemic that forced us to do more things via the internet. With all the unfortunate difficulties and struggles we had to face, let's notice the good part, the emerging and valuable opportunities brought to us as well. The great opportunity to enjoy the very best of sciences together, the opportunity of Christmas lecture. Let me welcome now our special and distinguished guest, Professor G. Stang, Distinguished Professor of the Department of Chemistry, University, Utah, USA, who is the foreign member of the Hungarian Academy of Sciences. Before I give him the floor, please allow me to briefly introduce him, whom many of us know him well. He was born in 1949 in Nuremberg, Germany, to a German mother and a Hungarian father, and lived in Hungary until 1956. Early on, he loved both mathematics and chemistry, prepared PhD indicator and gunpowder while living at one of the nicest places of Hungary, the Lake Balaton. He graduated magna cum laude as a BS chemistry in 1963 DePaul University, Chicago, Illinois, and get his PhD in chemistry at the University of California, Berkeley in 1966, and was a postdoctoral fellow at Princeton University between 66 and 69, where he worked as an NIH fellow with Peter Schleyer. His research interest is molecular architecture via coordination, formation of discrete supermolecular species with well-defined geometries and shapes via self-assembly, such as molecular triangles, squares, rectangles, pentagons, hexagons, and additional 3D assemblies. But of course, he is also interested in the biochemical and biomedical anti-tumor properties of related organometallic compounds. Professor Peter Stang is the author and co-author of 615 scientific publications, including 7 monographies and 2 dozens of reviews. He has an H index of 92 and a total citation of over 43,000 as December 1st of 2002. To date, he has mentored 90 postdoctoral associates and 40 students have obtained PhD degrees under his direction. In terms of professional societies, he is a fellow of the American Chemical Society and the American Association of Advancement of Sciences. And as well as we all know, he is the editor of JAX since January 2002. Today, the title of his talk is A Biological Self-Assembly, Pre-Designed Metal Cycles and Metal Cages via Coordination. Dear Professor Stang, dear Peter, the floor is yours now.
Köszönöm szépen, Percel úr. Jó estét kívánok mindenkinek! Szeretnék magyarul egy pár szót mondani, mielőtt elkezdünk. Nagyon örülök a meghívásra erre a különleges előadásra. Szeretnék mindenkinek kellemes karácsonyi ünnepeket kívánni, úgy, mint egy jó, boldog és egészséges új évet. Na most sajnos angolul kell tovább menni, mert nem tudom magyarul a kémiai szavakat.
Thank you, Peter. That was very kind and very fun.
Well, I speak 3 languages, all 3 with an accent. So I obviously didn't do this work alone. I need to acknowledge my co-workers. I've been working in this area for 25 years, and also the funding agencies, the NIH and NSF. Also, I'm not alone in this area. There are lots of other people. Here are some key references. Probably the major other contributor is Makoto Fujita in Japan. He's an excellent expert in this area. Now, there are lots of species: MOFs, COFs, supramolecular coordination complexes. I will restrict myself only to the supramolecular coordination complexes. I will have nothing or very little to say about MOFs or COFs, which are currently very popular areas. So let me give you an introduction, then talk about 2D polygon self-assembly, some functionalized systems, photophysics, surface confined. Then we go to three-dimensional systems, and we conclude with some biological activity, some quite interesting results we have in that area. This is the protein coat of rhinovirus R1. And like all protein coat, it's in the shape of a dodecahedra or icosahedra. And you can ask, how does nature do this? Well, nature does it by self-assembly, using nature's weak interactions: hydrogen bonding, hydrophilic, hydrophobic, pi-pi stacking, van der Waals interactions. If you want to use these weak interactions in the laboratory, there's a problem. Other than hydrogen bonding and maybe pi-pi stacking, they don't have directionality. And of course, you need directionality to form complex systems like a dodecahedra or an icosahedra, etc. And so we adopted coordination, metal ligand bonds, because they have directionality. So let's look at two-dimensional assemblies. As you can see, a square is nothing more than 90-degree shape-defining units connected by linear connectors, or two different 90-degree shape-defining units as indicated here. And so a triangle is nothing more than three 60-degree shape-defining units connected by linear connectors, as you can see here. Again, a square is four 90-degree units connected by linear connectors, or two different 90-degree units, and so on down the line. A hexagon, which you can't quite see because it's covered up, is, for example, 620-degree units connected by linear connectors. So let's make a triangle. This is a 60-degree angle, which has an acceptor platinum metal unit that I then connect with lone pair nitrogen units, such as bipyridine and some other systems. We do this in a mixture of acetone water. It's deuterated, so we can go directly to the NMR and check the molecules that we have. So here is the X-ray structure of the triangle, just to show you that, in fact, we have it. We know the dimension, the shape, the size, etc. Now, when we started some 25 years ago, we take ordinary platinum or palladium dichlorides, connect two of the sites by this phosphine so that it's restricted to this unit. Then we displace the chloride, which is not a very good leaving group, with a much better trifluoromethane sulfonate leaving group. And we have this unit, which we simply react 1-to-1 methylene chloride. And in a matter of minutes, we get this molecular square self-assembled. The isolated yield for the platinum is 96%. By now, this was 25 years ago, by now we get the palladium also in 97-98% isolated yield. And again, here is the X-ray structure. You can see the size, the shape, the dimension of this molecule, and proof that we actually have it. This is by now a very general methodology. There are dozens of people working in this area. There are probably maybe a couple of hundred molecular squares that people have made using this methodology that we have developed. And I just illustrate some of the molecules here. Now let's do something that seems trivially simple, but in fact, it's not as simple as it seems. Let's make a rectangle instead of a square. Now, to do this properly, we have to do it so that this part of the molecule reacts selectively with the short connector, and this side of the molecule reacts with the long connector. Then we get a rectangle. Otherwise, of course, we get a mixture of these compounds, and nobody likes mixtures. And we do not know, even with modern chemistry, how to be so selective that this reacts exclusively with the short one and this exclusively with the long one. So we do something else. We build what we call a molecular clip. We take commercially available dichloroanthraquinone, get the chloride, again, insert the metal, that's a common organometallic reaction, and replace the halides again with trifluoromethane sulfonate. We then have what I call a molecular clip, like this, that we will be able to connect, as you will see, with connectors, and there it is. There is our molecular rectangle. And here, once again, is the X-ray structure of this molecule, so we know exactly what we have. And notice again, after we exchange the nitrates for hexafluorophosphates, because it's easier to get a crystal structure, our isolated yield is 97%. And here again is just a molecular structure showing this molecule, a model based on the X-ray structure that we have. Now, what about neutral systems? So far, I showed you charged systems that have charges. And why do I want neutral systems? Well, they have different properties, different applications, different uses. So once again, the same exact acceptor molecule, that's a 60-degree angle, as you can see. And now I connect with dicarboxylic acids. So here are some examples of the dicarboxylic acids. And again, room temperature, by the time I mix these two components, in 2-3 minutes, the reaction is over and I get 97% yield of this molecule. And once again, here is the X-ray structure and a model based on the X-ray structure of this neutral molecular triangle. And you can see, of course, that the cavities are not empty. They're full of solvent molecules, as one would expect. Now, how does this all happen? And what is our evidence for self-assembly? So let's do an experiment where we make a molecular rectangle with all hydrogen bipyridine, as indicated here. And we make a molecular rectangle with all deuterium bipyridine, per deuterobipyridine, as indicated here, and isolate and characterize these two molecules. And we can do exactly the same with triangles. On all hydrogen self-assembled triangle, on all deuterium self-assembled triangle. Then let's ask a very simple question. I take these two isolated molecules and mix them. Do they scramble? Do they give me the mixed deuteropyridyl molecule? Do they scramble? And how can I tell if they scramble? Well, of course, by mass spec. So you can see starting time times 0, all hydrogen, all deuterium. After several hours, it's a mixture, and the same for the triangle. Now you see here, what's even more interesting is that I can take an all hydrogen rectangle and mix it with an isolated all deuterium triangle. Here is the mass spec, and I get complete random statistical mixing. And that tells me that these processes are under thermodynamic control, but kinetically reversible. And that's what makes them self-healing, self-correcting, so that I can always get the molecule. What I mean by that, let's look at this. See if, can you see this? Okay. So
Yes.
if I want to make a square, for example, and the pieces come together like this, that's not good. So it comes apart, comes back like this. Next piece comes in like this. That's not good. Comes apart, comes back like this. And that's what self-healing, self-correcting means, and kinetic control, but thermodynamically. So let's look at functionalized systems. So what I do is, again, make the same system, self-assemble it into a rhomboid or a hexagon, two different hexagons, and then I functionalize these connecting units. And I can put two in 180-degree orientation, functional groups, or I can put three in 120-degree orientation, or I can put six functional groups on this molecule in a relative orientation of 60 degrees. Now, what functionality? How about a fresh A-type Dendromer? So what I do again is this is a series of just organic synthesis where I take commercially available dibromophenol, protect the OH group, couple with the dipyridyl unit. That's 120-degree angle, as you can see there. And then, of course, I can now functionalize it with 0, first, second, third order dendrimers right there, and then self-assemble. And so here is the X-ray structure of a rhomboidal Metallo Dendromer system. So here you can see the Dendromer, here is the rhomboid, and here is the X-ray structure of that molecule, again, to show that we actually have the molecule that we claim. Again, it's a little difficult to see this because part of it is cut off, but here is a beautiful hexa Dendromer substituted hexagon molecule. I have grandkids who are young, 8 and 12 years old. And the grandkids call this a beautiful snowflake molecule. And that's what it is. If you look at it, that's like a snowflake. Now, again, I can put ferrocenes on these molecules. And I can put, again, 2 in opposite direction, or 3 with 120-degree orientation, or 6 ferrocene molecules with 60-degree relative orientation on these molecules. I can then do electrochemistry and ask a very interesting question. Do these units talk to each other? Do they interact with each other? Do they influence each other? And it turns out they don't. They're too far apart underneath here. And we know that because we get individual one-electron redox systems as indicated here. So they're a little too far apart to influence each other, communicate, and talk with each other. Now, what about a crown eater pseudo-rotoxane? And what's a pseudo-rotoxane? Well, it's a molecule where you take a cyclic system, usually a crown eater, and thread through it a dibenzyl ammonium molecule. It's a well-known pseudo-rotoxane system as indicated here. And again, we self-assemble with this 120-degree unit that carries here the crown eater. Again, part of the molecule is covered up. Here is the 120-degree building unit. And now I can do this experiment 2 ways. I can first self-assemble and then put in the crown eater. Or I can first put in the crown eater and then self-assemble and get the identical molecule. And it's always good to get to the same way, the same molecule, same species, 2 different ways. And here again, this is now a very interesting system. And again, the power of self-assembly. Anybody have a 2-year-old child? Somebody has a 2-year-old child. Chaba, how old is your baby?
Oh, he's just 2. He's just 2. Yeah.
He's just 2. What do 2-year-olds like to do? Mix everything together, right? Just throw, you give them food and they throw it all together. That's what we do. We just throw everything in a pot, all the building units, and it self-assembles into this molecule. And that, again, is the power of self-assembly. And that's, of course, why nature uses self-assembly. Now let's look at systems that are what I call multi-component. that have more than just 2 building units, that have 3 building units. So again, I have my shape-defining 90-degree platinum acceptor. I can then combine this with this dicarboxylate unit and get the homologated neutral system, or I can combine it with this dipyridyl system and get the charged system. And the question is, what happens if I mix all 3 of these together? Just again, put them all in one pot. And I get what's called the heteroligated system. Again, a little bit difficult to see here. And how do I know I have the heteroligated system? Well, let's take a look at this molecule. It has 2 phosphorus atoms here and here, here and here, here and here. And in these systems, those phosphoruses are identical. In this system, they're not. The phosphorus here on this platinum is different from the phosphorus on that platinum. And that's what I see. I see doublet of doublets in the phosphorus NMR for this molecule, singlets as I would expect for that molecule. In the mass spec also, of course, you can see that I can see the proper mass spec for these systems. And of course, these are high resolution mass specs, so that the high resolution matches with this is the calculated, this is the experimental high resolution mass spec, and you can see that the agreement is remarkable, and again demonstrates that we have the molecule that we claim. Well, let's look at some properties of these molecules, and let's look at photophysics and hierarchical self-assembly, and I'll explain to you what I mean by hierarchical self-assembly. So we make these 120-degree building units that inside, if I can find my mouse, that inside has this diamino functionality, and outside has electron withdrawing and electron donating substituents. I self-assemble this system into this rhomboid, and again, it has these substituents, electron withdrawing and electron donating substituents on this molecule. And here is just again the proof, the phosphorous NMR for this molecule. If I can find there it is, a singlet in the phosphorus, again, a well-matched high resolution mass spec that shows that I have this molecule. And what is interesting is that the emission these molecules emit span the entire visible range. So you can see, for example, that the nitro group is essentially in the blue region. The amino group is essentially, there is of course some overlap, in the red region in this system. So this is the emission wavelength, and it spans the entire visible region. And that, as we'll see, will be useful in applications. Now, what do I mean by higher order self-assembly? What I mean is that we use 2 of nature's weak interactions, not just 1. We will use coordination, and we will use hydrogen bonding. So here again is I have trouble, oh, there it is, okay. Here again is the 120-degree donor unit, and I've built onto this molecule a strongly hydrogen bonding unit, as you can see here. I then self-assemble, and I symbolize this unit here, this hydrogen bonding arm, with this little symbol here. And it self-assembles into a rhomboid that then has these arms that can further hydrogen bond, or I self-assemble into a hexagon, and again, it has these arms with the hydrogen bonding, 3 of them, as you see here. And again, just to prove how clean this system is, here is the phosphorus NMR, very clean, single sharp singlet as expected. Here is the high resolution mass spec of this molecule. And again, the match is perfect. And here it is for the hexagon with these arms. Again, a very sharp singlet in the phosphorus as I expected. And again, a very well matched high resolution mass spec for this molecule. And then what's interesting is that hydrogen bonding takes over as indicated here. And I get a one-dimensional rhomboidal system or a two-dimensional network as indicated here, where the little hexagons are formed by coordination and these large hexagons are formed by the hydrogen bonding. And this is a remarkable system. You can do all of this in 10 minutes if you have the building blocks, and quantitatively. And that again is the power of self-assembly and using nature's own weak interactions. Now, what does this system look like? Well, I had a very good Chinese postdoc, and he came to me with a vial, and he had a tweezer in the vial, and he pulled out this film, just like this. And here it is. There is the film, and the film is so strong that you can loop it, like you can see here. Okay, so that's just a looped film that you can pull out from this hydrogen bond coordination one-dimensional system as indicated here. Now, what about a dendroidized metallocyclic system? Well, we do the same thing. We now put the dendrimer on the back of the acceptor unit by standard organic chemistry. We build in this hydrogen bonding unit, which again I symbolize by this, and we self-assemble into this rhomboid by coordination that carries the dendromer on the back and is capable of further hydrogen bonding by these hydrogen bonding units and arms. And again, you see a beautiful network. We don't know if this is an oligomer or a polymer. That's very difficult to establish, whether we have 6 or 12 units or 100 units in this. But you can see that it carries the dendromer on the back and hydrogen bonding and rhomboidal self-assembly. We can do exactly the same thing with the hexagon system and get again a beautiful network, a two-dimensional pseudo-rotoxane polymer network system, where once again, the small hexagons are formed by coordination and the large hexagons by this pseudo system here as indicated in this PowerPoint. Now let's see if I can put these molecules on surfaces. And why do I want to put them on a surface? Well, for application, for a device, for example, it's easier to connect and to make useful devices if they sit on a surface rather than random. And I did this collaboratively with Chinese coworkers, and you can see that the molecular squares beautifully deposit on a gold 1,1 surface, and you can see the individual molecule in this unit. And here is our model of how this sits on the surface, on this gold 1,1 surface. We can also do this with the rectangle, as you see here. It forms a beautiful ordered system on gold 1,1 surface. Now, it's fairly easy to see where you can take a two-dimensional metallocycle system and put it on a flat surface. It's not so easy to see what happens if you try to put a three-dimensional system, because it can sit this way, or this way, or this way. And you can see that we can even put a three-dimensional system. I'll tell you how we make this three-dimensional system on a gold 1,1 surface, and it forms beautiful ordered networks on gold 1,1,1. And again, here's our model of how this sits on the surface of the gold. Now let's look at three-dimensional assemblies, which of course are inherently more interesting. A cage in a three-dimensional system is more interesting than a two-dimensional metallocyclic system. You know, in Hungary, in the 1950s, I had an excellent mathematics and geometry classes. And so I know what Platonic Polyhedra are. You know, they're three-dimensional systems where you take the same two-dimensional system. So 4 triangles make a tetrahedron, 8 squares make a cube. And the 12 pentagons make a dodecahedra. There it is, three-dimensional system. But those aren't the only ones. You can also get what's called Archimedean semi-regular polygons. And so Cubo Octahedra is made of triangles and squares put together, and that makes, of course, the closed systems. Now, when I give this lecture to young people, I also like to tell them, who plays soccer? And have you ever taken a close look at your soccer ball? And here is your soccer ball. Your soccer ball, if you take a close look at it, is nothing but 5 and 6-membered rings put together. And that makes a three-dimensional system. And that's a truncated icosahedra. That's your soccer ball, 5 and 6-membered rings. And I will show you how we can use this approach to make Cubo Octahedra and other three-dimensional systems. But it turns out that the synthetic organic chemists, who are almost geniuses, they can make almost anything, beat us to it. Günther Meyer in Germany, what is that, 40 years ago, made tetrahedrane. Phil Eaton in the United States made cubane. And Leo Paquette, the late Leo Paquette at Ohio State, made dodecahedrane. Now, this, of course, is the parent hydrocarbon synthesized. It took Leo Paquette 20 man-years, and 43 individual synthetic steps to make this dodecahedrane. Now, what's a man-year? A man-year is one good postdoc working 1 year. 20 man-years is 20 very good graduate students, each working 1 year. That's 20 man-years. I can make this system in a single step quantitatively by self-assembly. Now, how do we do that? Well, let's do a little retrosynthetic analysis. So a cube, for example, a cube is nothing more than 8 of these mutually perpendicular edges like this, indicated in green here, that I connect with 12 connectors. And I call that the edge-directed assembly because I first make the edge and then connect them with these linear connectors. But this is not the only way to do it. I can also do it by face-directed approach, where I make the face of a molecule. I'll show you later on what we do and how, and connect the faces and get the same cube as indicated here. So another way of looking at this is that if I have a set of tritopic angular systems, 60, 90, 109, 120 angular systems, and I connect them with ditopic angular systems, here are the three-dimensional polyhedra that I can get using this. And so again, I need to do some chemistry. I take bromopyridine, buy it, lithiated, reacted with this ketone, and get tris-pyridyl methanol. You can't quite see it because it's covered, but it's just tris-pyridyl methanol, where I have 3 pyridine units like this and an OH group sitting on top. And I simply ask a question, can I take 2 of these and connect them? And that's what here is the X-ray of the building unit. I'm sorry, I forgot. And that's exactly what we do. We take this clip that I told you about before, and we connect it with this tritopic ligand. And here is a trigonal prism that self-assembles. And again, in order to get X-ray crystallography, we exchange the nitrate with hexafluorophosphate because hexafluorophosphates crystallize better and it's easier to get an X-ray structure. And we had a very interesting experience. There's 6 of these counter ions, and when we exchanged, we could only exchange 5. We could never exchange 6. And I had a graduate student do this, and I said, go back and check it again. I'm sure it's exchanged. And he said, no, I can only see 5 counter ions. I gave it to a postdoc, and he came back and he said, I can only see 5. And we didn't know why until we got the X-ray, and that is because the last one is encapsulated inside the cage and cannot get out. Okay, so here is the counter ion encapsulated in that trigonal prism unit. Now let's make an Archimedean solid, a truncated tetrahedron. And what's a truncated tetrahedron? It's a tetrahedron whose edges I cut off as indicated here. And here it is. 2-to-3 ratio of this tritopic building unit with this platinum acceptor in nitromethane, room temperature 5 minutes, and I get this 95% yield of that truncated tetrahedron molecule. Again, a remarkable reaction. You mix these components and you get that beautiful complex molecule in essentially one step. And there is the X-ray structure of that molecule. So again, we know exactly what we have. We know the shape, the size, the dimensions of those molecules. We can also do a truncated system with a hexapyridyl system that's here, this molecule, which of course we have to synthesize. And I'll get back to this molecule later on for reasons you will see. And here is the X-ray structure of that self-assembled system. And again, we don't need to spend a lot of time. It's not so easy. That's why I need 2 glasses of wine every day, because with 2 glasses of wine, I can see this molecule much, much better. It starts dancing in my mind after I have 2 glasses of red wine, these beautiful molecules. Now, what about face-directed systems? And again, what I mean is I put this molecule, that's the face, you see? That's a planar molecule, and it sits as a face. And it gets self-assembled into a trigonal prism, a pentagonal prism, a square prism, a hexagonal prism. And the interesting system is this one. This is a trigonal prism as indicated here. And it's interesting because that system is chiral. And in fact, this is the interesting system, okay? With this cyclobutadiene system. And it's chiral by virtue of the fact that these 4 pyridine units cannot be planar. They're twisted. And they're twisted either counterclockwise or twisted clockwise. And of course, that makes a chiral system, and that chirality can be transferred to the self-assembled trigonal prism. And I can ask 2 interesting questions. One is, this cobaltocene that stabilizes the cyclobutadiene, do they face outside or do they face inside the molecule? And it turns out here are the 2 possible enantiomers. NMR and other data tells us that they face outside. And here are the 2 enantiomers of this molecule, the so-called PPP enantiomer and the so-called MMM enantiomer of this particular molecule. So these are chiral. And it turns out that I can separate them by putting it again on gold. So here you see is a complete separation. Here is one enantiomer, here is the other enantiomer. Now we don't know which is which because we have not been able to get an X-ray structure. We just know that one enantiomer sits down on one side, the other enantiomer sits down on the other side. Again, on a gold surface, here is our model of how that molecule sits on that gold surface. Now, what about a Cubo Octahedra? And I told you that a Cubo Octahedra is combinations of triangles and molecular squares. So here is our triangular building unit with this 120 degree. Here is the X-ray of that molecule. And what happens if I take this 3-dimensional object, a Cubo Octahedra, and project it on a 2-dimensional surface? Just project it like this on the surface. And what you get is this, a square that's surrounded by 4 triangles. So all I have to do is connect here, 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 and here, and I have my system, and there it is. That's a Cubo Octahedra. And again, a very remarkable reaction. You combine those 2 components, 20 individual molecules, methylene chloride, room temperature, within 10 minutes, we have a 90% isolated yield of that remarkable Cubo Octahedra molecule. What about, this is the isostructural one. Now, what do I mean by isostructural? Well, let's take a look. Here I have the donor pyridine units on this triangular donor unit and the platinum acceptors on this unit, and I can exchange that. I can take this platinum and put it here and the pyridines and put them there. And then I get the isostructural molecule, identical composition, identical molecular weight, but different connectivity. The connectivity is different. One connects this way, the other one connects this way, if you wish. And these are the largest man-made isomers, pure isomers known. And again, notice 99% isolated yield. Again, the power of self-assembly. I can functionalize these molecules. I can functionalize them, for example, with ferrocene. And I can put 12 ferrocene units on it. I can functionalize them with crown ether and then put crown ether molecules on this. I can then again do electrochemistry and look at the electrochemistry and get the diffusion coefficient of this molecule. And I'll tell you what that tells me later on in a minute. I can put a weakly fluorescent building unit on this. Anthracene is very weakly fluorescent. But when I put 12 of them on it, the combination of the fluorescence is quite remarkable. So I live in Utah. And I tell my people that if you go out in the countryside in Utah and you look up in the sky, that's what you see. Okay? This is not what you see in the sky in Beijing, because of course, Beijing is totally polluted. And this is, of course, the emission of that particular molecule that I just showed you. Now, what about a dodecahedra? As I told you, a dodecahedra is 12 pentagons. So I need to make pentagons and then connect them. And I need to have appropriate building units. And here again is this trispiridyl methanol molecule. Here is the X-ray of this trispiridyl methanol building molecule. I need a linear connector. Again, very simple. I buy diiodobenzene, insert the platinum, exchange the iodides for a better trifluoromethane sulfonate group as indicated here. Combine the two and there is a remarkable dodecahedra molecule. Again, remarkable reaction. 50 individual pieces come together. Methylene chloride acetone solvent mixture because they're better soluble in that mixed solvent. 98% isolated yield. Again, a very remarkable reaction to form this beautiful dodecahedra by self-assembly. Let's go back for a minute. This molecule has 120 phosphorus atoms. Okay, the phosphorus is on the platinum, 120, 30 times 4. All those phosphoruses are identical by symmetry. And that's what I see, a single sharp line with satellites, the satellite platinum satellites here, but a single sharp line for the phosphorus atom. That's part of our proof for this molecule. Then I can do something called the pulse gradient spin echo NMR, a well-known technique, well-known by polymer chemists, that allows me to measure the diffusion coefficient. And then by means of the diffusion coefficient, the so-called Stokes-Einstein equation, I can calculate the dimension of this molecule. And that's what you see here. Here is the experimental diffusion coefficient. Here is the experimental dimension. Here is the estimated calculated dimension. And again, you can see the agreement is remarkable between the calculated and experimental. I can also do, of course, STM image, TEM image. So here is a TEM image of a single dodecahedra. There is another one, okay, TEM image. So again, I'm pretty sure that I have this molecule. Time is running out, so I'm going to go a little faster. Again, I can use now 3 components. This is the top and the bottom of this molecule. Again, the platinum are the corners that holds it together, and these are the columns. And that's a 3-component self-assembly. Again, just to show you the calculated experimental mass spec. And then, of course, I can do a simulation calculated, measure the diffusion coefficient. And again, there is reasonably good experimental agreement with the calculated dimension and the experimentally measured dimension of this molecule. And I can, of course, use any number of tops here. For example, this porphyrin-like molecule or this tetrasubstituted ethylene molecule as the top and the bottom of this molecule. And again, this is just data. Don't spend too much time looking to convince you that I actually have this molecule. And here are a number of examples that I can make. Remarkable, again, that I can make these trigonal prisms, square prism molecules with different tops and bottoms on these type of molecules. Here are 4 molecules that I made, a hexagonal prism molecules by using, again, this molecule, which is not so hard to make by cross-coupling reactions, standard organic chemistry, the edges, the connectors, and then, of course, the columns. And what this illustrates that I can make my hexagonal prism this big, or this big, or this big, vary the dimension of it by simply varying these dimension of the column from a relatively small bipyridine molecule to this relatively long azodicarboxylate molecule. And again, here is data showing that I have this molecule mass spec and phosphorous NMR. I can functionalize these molecules, and I can functionalize them one of 2 ways. I can pre-functionalize my building units, as indicated here, standard organic chemistry, and then self-assemble, and now I have functionalized system. Or I can first self-assemble, put on this unit here, and then post-self-assembly functionalize. And again, of course, there is interest in functionalized molecules because they're much more useful and have much more potentially interesting applications. Here is a very interesting molecule. This is a Penta double prism. It's not so easy to see that, but if you look very closely, this again is self-assembled from these 2 components. What this is a prism within a prism, okay? A penta prism, a prism inside a prism. Here is a hexagonal prism again. Now, again, I have to be honest. I have to make this by standard organic chemistry, but then I just simply mix these 2. And again, a hexagonal prism within a prism, 2 prisms inside. It's like a Russian doll. What do you call these dolls where you have several dolls inside a doll inside a doll? Well, this is a prism inside a prism. Now, you know, NIH supported this work for about 20 years, just basic research. And then they said, well, you had enough fun. What are these things good for? What can you do with them? Why should NIH support this work? Just for you to have fun? Well, let me show you what we can do. If you have a cage, you can put something inside, host-guest chemistry. For example, a parakeet inside a cage, right? That's host-guest chemistry. And here is this truncated system, tetrahedron that I showed you and showed you the X-ray. And I can put 3 of these guest molecules inside here. Okay, I can encapsulate 3 guest molecules inside the cage. So that's host-guest chemistry. Now let's very quickly look at some applications of these molecules. These molecules have very interesting anti-tumor properties, and that's why NIH supports this work. So here is a ruthenium rhomboid system, and you can see that the tumors shrink considerably when we apply this molecule to a mouse. Here again is an anti-tumor activity of a platinum compound. And again, I told you that these molecules emit, which is very nice because I can see exactly where those molecules are in the mice, and I can see exactly the diminution of the emission and therefore the shrinking of the tumor in these molecules. And that's, of course, very important and very interesting. So here again is a platinum rhomboidal system whose you know, we have platinum, palladium, and we vary some of the building units. And again, it's a little hard to see this, but we have 3 cancer lines here. And cisplatin is the commercially currently most widely used anti-tumor agent. If somebody has cancer, unfortunately, they usually treat them with cisplatin, very well-known anti-tumor agent. So we compare the activity in these cancer lines of our compounds with cisplatin. And you can see that in some cell lines, our compound is better than cisplatin. And that's very encouraging. And that's, of course, why the NIH supports this. Now, anti-tumor activity of rhomboids, again, against HeLa cells. I don't want to go into the details of this picture. Anti-tumor activity of a triangle again. The time is running out, so I'm going to go a little fast. Again, animal, we do mice testing. And again, what's very nice is that we can tell where in the mouse this is because it emits. And so we can tell, for example, that it goes into the breast, it goes into the ovaries, etc., in the mouse and where it resides. And again, you can see here what happens after treatment and how the tumor shrinks after treatment. We can also deliver drugs because we can enclose this into this hexagonal molecule, guest molecules, as I showed you. And we can enclose a drug molecule, which then gets delivered to the mouse tumor. And that's, of course, what we want, is specific delivery to the tumor cells, not the healthy ones. And that's what we're seeing here. Some selectivity, delivery to more selectively the tumor cell than the normal cells. So here again, we have one of these rectangles. And again, the activity, which is, unfortunately, it's blocked, comparable or better than cisplatin. And here again is a system where we made this 3-dimensional system and compared it against 5 cell lines compared with cisplatin. And again, you can see that our molecule has activity, which is double the activity of cisplatin, better than cisplatin, comparable or better than cisplatin. And that's very, very encouraging. Now, I want to emphasize, of course, that we are far, far from one of these being a drug, because you obviously have to do clinical studies, extensive clinical studies, prove not only efficacy, but safety. But it's not impossible that in 5 years, one of these molecules will be a new anti-tumor agent. Now, in the United States, we have something, a picture is worth 1,000 words. Here is a living mouse. That's a living mouse with this tumor, which later you can kill the mouse and excise the tumor. And when you treat it with this molecule, the tumor shrinks. And again, exceedingly encouraging. We are very delighted that we have this activity, and we are very pleased, of course, that as a consequence, NIH is supporting this. And who knows, one of these days, one of these may become a drug. Finally, I'd like to show you the laboratory where we do this work. This is the laboratory. You know, in Europe, you have 2,000, 3,000-year-old history. You have cathedrals that are 1,000 years old, magnificent palaces that are 1,000 years old. We don't have anything like that. What we have is unique national parks. And Utah has 5 of them. And this is Bryce Canyon National Park, one of the most unique, most beautiful national parks in the United States. And I invite every single one of you, come visit me in Utah and I'll take you down to Bryce Canyon National Park and show you the beauty of Bryce Canyon. Nagyon szépen köszönöm, ez a vége.
Thank you, Peter. That was really outstanding. So we really had the opportunity to see from the building blocks up to how self-selection and complex things emerges. So I think it was a wonderful talk, and I think it's just great. Before we leave you, I'd like to hand over. Currently, this looks virtual, but it's not. So this is your diploma, and if I may ask somebody, they can help you. So they put it on a screen.
Okay.
Okay, so you'll see now. Yeah, that's it.
Yes.
And I'll read it.
Yes.
So this is a certificate of appreciation. The chemical science section of the Hungarian Academy of Sciences is pleased to present a certificate of appreciation to the internationally renowned scientist, Professor Peter J. Stang, foreign member of the Hungarian Academy of Sciences, in recognition of his outstanding contributions at Christmas lecture to advanced chemistry sciences in Hungary. And this is in English, and because this is an old university, this is also, on the right, you'll see, in Latin.
Thank you, András. Thank you very much. I really appreciate it.
So this looks virtual.
Actually, I do.
If you open your mailbox, you already get a copy of that. So that was quick.
Okay.
But the physical one, we'll mail it tomorrow. And
Great.
so hopefully, maybe you receive it this year or next year as one of the first important things.
It will be a pleasure whenever it comes. If it comes this year or next year, it'll be a pleasure. Thank you very much.
Absolutely. So I think with that, it's about to close our first chemistry lecture. So let me close. We had a wonderful night. Our first Christmas lecture, I think, was really outstanding. And let me thank Professor Stang once again, his outstanding lectures. And the only thing I'd like to finish with is to wish you all a Merry Christmas and a very Happy New Year.
Thank you very much, and same. Merry
Thanks
Christmas.
for everybody. Thanks for coming.